be able to watch them later. So today I'm going to, talk about actually in the next probably several lessons, I'm going to talk about mainly math and calculus basically. So I try to show you simple calculus concept, and then how we can use simple math to do quite interesting stuff. And quite something like how do we know the sphere's volume is 4/3 pi r cubic? So why is 4/3, and why is a sphere's surface is 4 pi r squares? Those kind of questions. And we can also talk about combined with a little bit like Newton law of physics, we can do some quite other interesting calculations. Some great example. So you don't really need any foundation to learn the basic calculus. And so who has already learned some calculus so far? And Leo, right? Okay, only Leo. Okay, so but that's good actually, Leo, and I hope it's it's a simple for you, but it's still insightful for you. So because one of my interests or my hobby is collect some really interesting math and physics problem which can be solved by simple calculus. I feel I think in the personally, at least my personal perspective, I think the calculus is one of the most powerful tool, and to show how much you can do with simple math, and then to solve the real world problem. Okay. So here, I hope I can use a fancy writing tool next time, because I'm buying a document camera which can project, and I can really do the writing formulas and derive formulas on paper. In that way, I can write with a pencil rather than right now. Right now, I have to do on the whiteboard with mouse or with the fingers is really awkward. But anyways, that's for this time. Let's still do this. I cannot write too small because of this. I have to write a little bigger. But next time, I hope I can have a little bit fancier setup. Okay, so let me switch to a whiteboard, so we can start to talk about this. Okay. So if you have any question, just feel free to ask. Okay. So there's many ways we can start talk about calculus. But the first thing I like to give you a small example, so you can get a sense rather than it's too abstract. Okay. So this example is, let's say we have a tennis ball. Okay. So I hold a tennis ball, and then I release my my hand. So the ball will fall towards the floor, right? Okay. So this process. So I start with we use the position. I start with the height is, let's say, 0, and then falling down. And so now we go like the after first second, after the second, after third second, and then fourth second, fifth second. Okay, coming, from your real life, as a spinning up, right? So I like to say this falling distance, of course, is a function of time. Let's use as S. Okay, S. So if you learn a little bit of physics, this formula free fall. We call it free fall. Right now, don't worry. Okay, I write down the formula. I don't need you to know why is this formula, because we will come back to this one later. So it's basically this formula, okay? So as the falling down the distance with time is 1/2 time g times t squared. It's a function of time squared. And so that's why it's speeding up. It's faster, going faster, and going, same within the same, for example, 1 second, the travel longer distance because the speed is higher. So the g is basically acceleration on Earth's surface due to the gravitation between any subject and the Earth. So the g is let's just use random approximate number is 10 meter per second square. Okay. If you don't fully understand why this is right now, it's not important because I just use this example. I will come back with more explanation later about Newton law and the physics. So anyway, g is about 10 meter per second square. Okay, and the real number should be about 9.8, but let's use 10 for simplicity. So in that case, we can calculate. So of course, at time 0, right? This is time 0, right? This time 1 second, 2 second, 3 second, right? Okay. If you have any question, just jump in. Okay, no problem. So now basically, as 0 second is 0, right? That's our origin, our starting point. Now, what is 1 second? Yeah, based on the formula, right? And 1/2 times 10 times 1 second square. And of course, you need when you do the physics calculation, you need to pay attention to unit, right? You cannot use different unit you have to use a consistent unit system. So in this case, also consistent. The second is meter per second square, right? So basically, the first second is 1/2 times 10 meter per second square time 1 second square, right? So that is 1 second square. So in that case, leading to 5 meters. So basically, after 1 second, the ball will fall down 5 meters from the original location. Okay, got it? So if you don't understand this formula, don't worry about it. Okay, later on we'll come back. I just want to use this one for now. So then, what is a second? The second after the second 2 seconds, you can use the same formula 1/2 times 10. Let me omit the unit because I already know the unit consistent. So in that is 2 square, right? So that come to what? Come to 20, right? 20 meter, okay? If you do this, S3 will be 45 meter. S4 will be, let me see, 8 meter. S5 will be 125 meter, I think, if I didn't calculate it wrong. Okay, got it? So basically, you will see that every second, if we use that 1 second as interval, so the first second we traveled 5 meter. This ball traveled 5 meter, the tennis ball. The second it traveled 15 meter, right? The third second traveled 25 meter, right? The fourth one traveled 35. The fifth second traveled 45 meter. Okay, got it? Okay. So now my question now is, so what is the speed of velocity at, for example, at exactly 4 seconds? Okay, at time of 4 seconds after I release the ball. So what is the velocity or speed? Can you do that calculation? Give a try. So let's go to the next page. Now basically at t equals 4 seconds after release the ball, what is velocity of speed? So basically, what is speed? Speed is, distance traveled at a certain time, right? So that distance. So in that case, so how we do this? If we go back saying, oh, let's use, let's use 4 second, and even 3 and 4 second, right? If you say, oh, my speed is at this 4 second, this speed is the ball traveled from the, the distance from the 4 second minus 3 second time 4 second minus 3 second, right? That's within 1 second time traveled how much distance? So 4 by 3, so that is 35 meter, correct? So that's 35 meter. So in that case, you are giving me 35 meter per second speed, right? At roughly 4 seconds is time, right? Correct? But if I say, okay, if I don't pick that 1 second, I pick 2 seconds. I pick number 5 minus number 3, right? This I pick the 2 seconds from time at 3 seconds to time at 5 seconds. So it's S5 minus S3. So this is what? This is, go back. This is 45 minus, no, sorry, 125 minus 45. So 125 minus 45 distance, 2 seconds. So that gave you what? 40 meter per second. So which one is right?
I mean, both are average speeds, so both are right.
So yeah, so basically, so that's we come down to, okay, what is speed? Speed is, here is basically, we call it average speed. That's why I put a bar on top, because it's really depending on what segment of time you talk about, right? So here, basically, if I use different time intervals, and I get a little bit different result, right? But do we have a accurate result? Do we have an accurate result? So this is basically the first question. I think Isaac Newton want to in 1600 when first tried to address this movement issue, and came out, and so that is why he realized, wow, realize is, wow, my mass is not, so available mass too is not enough. So that's why we needed to invent a little bit fancier mass tool. So that is what I'm going to talk about today. Okay. Anybody had any questions so far I talk about? You have to ask questions if you have, okay? Otherwise, you are not able to follow closely with me, okay? Because I assume you understand what I'm talking about, everything. If you not, ask question. There's certain assumption I don't need to know for now. For example, why the formula is 1/2 times g times t squared. You don't need to know that. Assuming that is correct. Everything else I derived here, you have to be crystal clear, okay? If you have a question, ask, okay? So now, so how do I know? How do I determine in this case, any moment after I release the ball, and what is the accurate true speed or velocity? How do we know that? Because if I used here 1 second, I used 2 seconds, how about I use 0.1 second? Can we do 0.1 second? Oh yeah, we can do 0.1 second, of course. You can calculate, for example, 3.9 second this travel distance, and then use the S4 minus S3.9 second, and divided by 0.1 second to calculate that one. You can try, right? So is that good enough or not? So that's why actually So let's do, because you guys already learned algebra, right? Everybody learned algebra. So let's do this. Let's say velocity is distance divided by time, right? Interval, time interval. Within 1 second, travel how much distance? Or 2 seconds, or 0.1 second, 0.1 second, or 0.9 second, whatever. Corresponding the interval on the bottom, and corresponding distance traveled on the top. In this case, so what if we just do algebra, I don't use a concrete number. So can we do this? Right? Can we do this? How to do? So basically, we're saying, okay, I know the formula is 1/2 gt square, right? And since I see that we traveled by delta t time, right? So really means, you know, so really means, so this one has to minus something, right? So this is t, let's say this is t0, this is t1, right? So this is basically, let me use eraser. This is really the t, this is really the t1 minus t0, correct? Right? Correct? So let's see this let's see this t1 minus t0 is delta t, okay? And then, which really means t1 equals t0 plus delta t, correct? Since t1 minus t0 is delta t. Got it? Clear? No problem? Okay, now go. So this is t0 plus delta t minus, correct? Good. Okay, can you calculate this one? Can you calculate this one? Right. So that is 1/2 g t0 square plus 2ab, basically g t0 delta t, right? Then plus 1/2 g delta t square, right? I open up this parenthesis, and it's a minus 1/2 g t0 square, correct? Clear? So now this one cancel out, correct? Okay, now you do this divide. So this one also cancel out. This one becomes 1. So eventually it becomes g t0 plus delta t, correct? Only 2 terms left. 2 terms left, okay? Any problem here so far? No problem. So we are, this is a very simple thing, and we are move faster later. I hope you capture every step. Otherwise, you're going to miss. Going to later come back saying, "Oh, I couldn't follow anymore." Okay, okay. So this is average speed. Use just algebra. I don't give you concrete number. Before we use 1 second, 2 seconds, 3 seconds before, but here is just use a letter to represent the whatever number it is. This t0 can be any number. T1 can be number. T0 can be 2 at 2 seconds. T1 at 4 seconds or whatever, right? Okay. So now, what does it really mean? This means we see that we did like use 1 second or 2 second intervals, and we got like one got like a 45 meter per second, one got like 40 meters per second, right? So do we have an accurate way to say the speed at exactly 4 seconds? Yes, we do. So that is basically you have here And if delta t and approaching to 0, so what this one becomes? So delta t approaching to 0. Here is an gt0. gt0 is always there. It's not related to how much delta t you choose. You choose 1 second, 2 seconds, 0.1 second, or 0.001 second. The first term doesn't change, correct? But the second term, var, when your delta t go to small, this one will keep going small. If you go into delta t is 0.000000001 second, so this will become really, really small. So eventually saying when delta t equals approaching to 0, we call the limit, and this term is gone, correct? Approaching to 0, right? So that's why now speed at t0 is really gt0. So really means at 4 seconds, t0 is 4 seconds. So the velocity, the accurate velocity should be 40. Correct? Because g is 10, right? True?
Our calculus teachers call this the poop equation because essentially everything you do is just to cancel out everything just like poop.
Right. So this is basically we write here, we rewrite it just to confirm. Okay, this is called average velocity is average distance traveled by average time. However, when I use delta t approaching to 0, called the limit, okay, delta t equal to 0. In this case, we come result as gt or gt0, whatever the t it is, correct? This is formula, right? This is what we derived, and so in math, actually this is symbol not invented by Isaac Newton, but rather by Leibniz, a German guy, and who co-invented this called calculus with Newton roughly the same time. So basically, when this one approach to 0, exactly 0, this one, we use delta right in this form. Okay. Now I use the small d, note the Greek form of delta. So this is small lower letter d, we call it delta. Okay, also delta. So the ds dt, we call it ds dt, is basically called derivative. In Chinese, we call 微分. Okay, so the meaning of derivative is basically this. Got it? Basic this. You have done this delta t approaching to 0 kind of this treatment. Got it? So really means that for a function like 1/2 gt squared, right? ds dt, which means this function's derivative equals gt. Got it? This actually is speed, instantaneous speed, we call. The first one is travel distance. The second one is speed. Okay. Now basically at every second, what time after release the ball, I know the speed at every that particular moment with accurate number. There's no ambiguity. Here is GT. Okay. So this is basically I introduced the very simple from this example called introduce the concept of derivative. Basically, it's a limit. So now I like you to do an example with me, right? I like you to do an example with me. Basically, is so now we have velocity is time function is gt, right? Correct? And I would like you to continue. So basically now I have the velocity, but I want to know acceleration. Acceleration, the definition A is called acceleration. Acceleration definition is dv delta v delta t. Within certain time interval, how velocity change. Before was how distance change was the velocity. Now is how velocity change is acceleration. But I also want you to do a same thing, delta t approaching to 0. Therefore, we can write it as dv dt. So basically, as acceleration becomes dv dt. Can you everybody take a piece of paper? Can you use the definition we went through, the process went through, to calculate what is acceleration of v when v equals to g times t? Can you do that? So
I want to.
Yeah, you don't need to raise hand. You just ask. It's fine. Sometimes I couldn't see you. I don't have everyone's the screen here.
So I have a question about like the derivative of ds dt. So the derivative of ds dt equals to gt, right? As you mentioned.
When s equals 1/2 gt squared, correct?
Okay, so that means if we're trying to solve the problem where let's say the tennis ball is at exactly time 4 seconds, right? So do we just need to use gravity, which is let's say 10, and times by time, which is 40?
Time 4. I mean, yeah, time 4 is 40. Correct. That's a velocity after you release ball after 4 seconds. That speed is roughly 40 meters per second. Depends on what G you use. When you use G is 10, is exactly 40. When you use G is 9.8, it's a little bit less than 40. Yeah. Okay. Can you derive this one quickly? Say what is acceleration going to be based on the velocity equals G times T. I give you just 1 minute. Okay, then I come back. I'll do this. Just use what's the definition, right? Go back to my definition. My definition is basically, if you really look at how did I? This is basic definition. Okay, so everybody can do it, or you have question? Do you want me to do it? Basically, okay, let's see. Let me do it. So A equals to delta V delta T, and when delta T approaching to 0, really means, so we have G T plus delta T minus GT divided by delta T, and then delta T need approaching to 0. Okay, in our case, where it becomes, so GT plus G delta T minus delta T divided by delta T, say GT cancel out, delta T cancel out is G, nothing else, correct? So basically, you see, acceleration is G, okay, which is 9.8 or 10 meter per second square, okay? So this is basically saying that if in this case, when the distance discrete function is 1/2 g times t squared, really means the acceleration is a constant g. So that's called free fall. Okay. Of course, I don't need you to understand why is 1/2 gt squared. You just know, okay, if that's 1/2 gt squared and everything is correct. Got it? Okay. Now I want you, if you're able to understand this, now we're going to give another small example like you to try. Before yeah, I want to slow down a little bit. I hope you guys able to. This is really important. Even though it's like I just spent like what 20 minutes to describe this whole concept. It's quite simple actually, but you needed to be. So let's say so we have a function, right? So let's say the function is a cube, x cube. Can you do as derivative? Really means df dx. Can you try? The definition, of course, is d delta f delta x when delta x approach to 0, which really means x plus delta x cube minus x cube divided by delta x, and delta x need to approach to 0. Can you calculate this one? See what is? No, I try to extrapolate into a general function, any function, right? I start with distance as a time function, 1/2 gt squared. Now I generalize to any function fx. F is function of x. Now I give you a x cube, this kind of function. And can we do the same thing? Calculate as a derivative. Yeah, take a piece of paper to calculate, okay? It's not hard. So this is basically x cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed minus x cubed, correct? Got it? Of course, you need to know the a plus b cube power 3 formula, okay? If you don't know, you just do a plus b times a plus b, and then time another a plus b, okay? So now the x squared, x cube cancel out, right? And then everyone has delta x cancel out. This one can become 1 power 1, this one become power 2, right? So now if the x approaching to 0, this one is gone. This one, of course, is gone. And the only thing left is, so the result is 3x squared. So really means to x power 3, the derivative formula becomes, you take the power 3, number 3 move to the front, and then the power 3 minus 1 become power 2. Okay. Got it? Then of course, if you this one do a derivative again, what's that? So basically now if you say, oh, my g function, oh, I can use another number. If I now is a phi function, a phi function is 3x squared. So what is this guy's derivative? So the result will be 6x. So which is 3 times 2x1. So it's 6x. Okay. So there basically you can calculate all kind of different functions using the process I went through to find out the derivative formula for each different type of function, right? So basically for power xn function, this guy's derivative. Sorry, this is really n. So that is n times x n minus 1. You can prove that. You can prove that. So
it's called power rule, right? There's like
this is called power. It's actually, if you know how to derive it, it's really easy to understand why, right? Got it. There's a later I can introduce a YouTube video can really concrete tell you why is you know, put it into a picture why is this case, but I don't want to go over here. So you, as long as you remember the process we went through, then you got it. Okay, got it. Okay, now can I give you another function? Let's say you try. How about the sine x? Can you do this guy's derivative? You try. So in this case, you need a little bit of trigonometry. You haven't learned trigonometry, then you probably won't be able to follow. But I assume you learn a little bit trigonometry. So that's basically.
Nothing. I'm just saying trick properties.
Yeah, there's a trig property. It's very simple as well. So basically, still delta x, now sine x plus delta x plus delta x minus sine x, right? Then delta x approaching to 0. So in our case, will be sine rule is sine x cosine delta x plus cosine x sine delta x minus sine x, correct? Divided by delta x. Sine, cosine, cosine, sine.
Wait, why is that?
Oh, you have you learned about sine trigonometry?
Not this part of it, I don't think so.
Yeah, you have to learn. You have to go back to learn trigonometry. Yeah.
I learned trigonometry algebra 2, but they didn't teach this part of this thing, like about sine x times cosine, when there is just sine in the equation.
All right, you need to learn more trigonometry.
I think is sine A plus sine B equals to sine A cosine B plus cosine A and sine B.
Correct.
That's the equation.
Right. So you need to learn more trigonometry, okay?
Mind saying it again, Leo? Sine A plus sine B equals to.
Wasn't me.
Oh.
It's me.
Oh, sorry.
Is sine A times, so sine A plus B equals to sine A times cosine B plus cosine A times sine B.
Yeah, that's what. Yeah, exactly. So basically, A here is x, B is delta x. So sine x plus delta x is sine x cosine delta x, cosine x sine delta x. Okay. Got it?
Well, I can, yeah, got it. Got equation.
Mm-hmm.
You can look up like trick cheat sheet on Google, and there's like all those like trick properties.
Right.
Yeah.
And also like you can look up calculus cheat sheet, so that all the like power rules and like quotient rules and like all the stuff like the derivative of sine, derivative of cosine, even like cotangent or like secant, something like that. So and it's
yeah.
So
okay, so this case, if you do this calculation, basically now you you have actually, you split it into two different combination. One is sine x time cosine delta x minus 1 divided delta x plus cosine x times sine delta x divided by delta x. When delta x equal to 0, eventually I don't need to go over proof here. Eventually this one equals cosine x. So really means sine x, the derivative is cosine x. Okay.
Wait, y is equals to cosine x in this case?
You need some you need a little bit more calculation, and you can I don't want to explain here, but you can find somewhere later on to explain this. So it's again, you need a trigonometry knowledge. Okay.
Okay.
Got it. So this is basically the some simple trick calculation, simple derivative calculation. So now I'm going to come back to this case. So let's still, so remember our initially S is 1 gt squared. V is ds dt. Sometimes we write into this way as a dot on top, really means derivative. Or some people write as this way. But anyway, both means, in calculus means derivative. So this one becomes gt. And then acceleration is dv dt. And basically is v dot core v equals g. Got it? So what does it really mean? I go back to here. So basically saying that this is, if we graph it, so this is a parabola, right? Parabola shape. So this is gt squared, correct? Okay. Now this is velocity. This is acceleration. So what is velocity from the graphing point of view? What it really means? Remember we were doing delta t, and we were doing some change here, delta s, right? So when delta s divided by delta t is really the average here, a slope, correct? If you look at that small triangle, horizontally moving, change delta t, vertically change delta x divided by delta t is basically the tangent that theta, right? So look at here, delta x, delta s, so this is theta. So delta s divided by delta x, delta t is basically tangent theta. Got it? Really bad. That's why I hope I have the better tool. So basically I'm saying that, so if you look at that small triangle I was drawing there, on the horizontal you change delta t, vertically you change delta s. The angle here is called theta. So tangent theta equals delta s divided by delta t, correct? Which is slope. So really means the derivative here is calculate all the individual slope at each individual point. So that becomes a line called GT, is a straight line, correct? Again, the acceleration is calculation slope again, because that's dv dt. Calculate this slope again. And But here, because it's straight line, the slope is constant. So that's why this one is G. Or here, G. Here. So its derivative is basically on the graph is trying to, if you the function you draw is a curve, the derivative is basically a slope calculation based on every around every dots around the dots on that curve. Got it? So that's so basically derivative is the slope. Okay, this concept. Okay. This is so basically the rate change, how fast it change, right? That's why delta S over delta T is means in changing 1 second, how much distance change. Change 1 second or change 0.1 second, 0.001, how quickly the distance change and the velocity change are those are the derivative. That means the yeah slope. Okay. Any question? Any question so far? All clear? All clear? Okay, now, let me go to next. So again, I like to redraw everything here. So basically we have S, T, V, T, A, T. This one is a parabol. Let me see. Yeah, parabol. This one is a straight line. This one is constant. G, GT, 1/2 GT square. Okay. So this is basically S equals 1/2 GT square. V equals ds dt equals GT. A equals dv dt equals G. So if from here to here, from here to here, is continue doing derivative. We did it twice from distance eventually leading to acceleration. Now, how can I go back? Okay. Really means in the real world, you know, real world, we know we are living on. When I throw an apple, release apple, you know, tennis ball, free fall. I only know. I don't know this formula. 1/2 GT square. Somebody told me. I never learned that. And however, what I know is on Earth's surface, the acceleration is a constant, and which is a g. So what I know is I only know a equals to g, correct? If I release a ball, no matter is you know, a tennis ball or apple, and it's free fall, what I only know is its acceleration is a constant is g. In that case, can I predict any time after I release its velocity, and also knowing the distance traveled? So which means I'm going backward. I need to go from knowing the acceleration. That's the only thing I know. And then I will go back. So what it really mean?
You interpret it.
What does it really mean? So this is basically the another concept called integral. Integral is a reverse of the derivative. So basically, you see the curve. I'm going from the bottom curve to bottom curve is constant, you know, number, going back to, I'm going this way now. Going this way. How do I do this? How do I do this? How do I do this? And actually, if you
Essentially,
really,
the area under the curve.
Yeah.
yeah. So yeah, I don't want to jump too quick because you know, you learned this one before. It's easy to understand, but for the newcomer, is a little bit sometimes hard. Okay. So actually, if you really look at here, the, you know, so really look at here is this area. So at equal t, what is this area?
It's literally just GT.
Yeah, it's GT. It's basically here. So basically, if you calculate this area, it give you the GT, correct? So basically, that give you, and then if you calculate this area, what it give you? So that give you
It's 1 over
1/2 of GT squared. So really, the, you know, the reverse way look like you are doing some kind of area, you know, integration, and go back. Okay, so that's called the integral. Let's go here. So it really means that right now we have acceleration equals to g constant, right, which is constant. And meanwhile, I know I have the formula a is dv dt, correct? Which means equals g. So basically, really means that this one dv dt and dt approaching to 0, correct? Okay, now from here I can say dv equals g dt. Can you understand this part? Can anybody understand this part?
Can you repeat it one more time?
So basically, I'm doing some, yeah, just some treatment. So basically, dv equals g times delta t, right? Delta v equals g times delta t, right? Correct? But if I using this derivative concept, which means delta t approaching to 0, I write small letter d dv equals g delta t. It's just like this one time over come this way. Got it?
It's like the same thing as before, but you're working with, like, I guess, instead of like working with you're working with
Right.
something much, like, actually,
Right.
I'm at a loss for words.
Oh,
Like something
I think
much.
it's like, let's use like the velocity and distance formula. So if like the velocity is constant, you can, and if you want to find the distance or displacement, you just use velocity times time. But I think what the integration is really comes in handy is when velocity is not constant. So like, let's say velocity is an equation, and if you integrate this equation, you can just you can figure out the distance with respect to time.
Right. Okay. So this one, anyone has issue with this case? So now basically in mass, so now we have here, okay? So what we do is called integral. It's like a big S, sum. It's basically saying that from V0 to V, or T0 to T, I integrate the you know, area underneath that curve. Got it? This allow us basically go back. That's exactly we try to go back here. Remember, we try to go back here. And how to do that? So basically, so this eventually give you V equals to GT. Introduce basically the integral concept is I mean, like, don't make it too complicated. So integral concept is a reverse process of derivative. But using so basically just like here, if I know the my acceleration is constant, in order to calculate the speed at a certain second, I need to keep integrate the area here until I hit the time I want to know the velocity about. So that eventually translate into GT. So that is so you have to basically, so this is called the integral sign. It's like S stretched into this called S. Basically, it's like if you like sigma, sum them together. Okay, S is means sum them together. So that is integral. You know, the sign. So that is how you do. So basically, when people saying that, you know, I have acceleration equals g, which is dv dt, I need to do reverse process. So that is people saying, okay, dv equal g dt, and then I need to do integral. And so going through the reverse process, this becomes v. Actually, it's a v minus v0 because it's from v0 go to v, because v0 is zero in the beginning. From the when I release the ball is 0 speed. So this one go into constant time t minus t0. T0 is also 0 when I release time. When I release, that is t0 time. So that gives you v equals gt. Got it? So that's basically that's so that's basically the one you understand the so compared to integral, the concept, the derivative concept is simpler. Derivative concept is like, oh, it's a, you know, ds dt when dt equals approaching to 0. For the integral concept, is a reverse concept. Therefore, you know, especially we use this sign. Sometimes you have a little bit problem to understand, but never mind. Get used to it, so you are get there. Okay, eventually we'll use some example to learn this. Okay. Okay. Is that good? Any question? Is that okay? Okay. So basically now I'm saying that we have a function gx, which is okay. Let's say gx is f function's derivative, right? Just like velocity is distance 2 times derivative. Acceleration is velocity 2 times derivative. And so once we know this, we can do an integral calculation. Okay, we write this way, and then we do integral. Okay, so this one give us fx to something. Got it? So that's basically doing a reverse derivative. Got it? So that is how you do it. Okay. So if we do reverse derivative, we know that fx equals x cubed as derivative x dots on top. That means derivative equals to what? 3x squared. Correct? Got it? So now if I have a gx equals to 3x squared, and I want to do integral, finding something, finding a hx which is equals to basically no. So basically this one is a derivative of this function. So what is h? Got it? Got the idea? So basically, it's so this is dfx dx. Okay, so I have a function fx. Derivative means dfx do the dx. So that equals to, for x cubed equal to 3x power 2. Now I see I have a function power 3 times x power 2, and which is some function's derivative. Can I know that function? So this is basically doing an integral. But you already know this is x cubed. So really means d.
How?
So really means dhx dx equals to 3x squared, correct? And how we can find hx? That's called the integral. Okay. So that is basically the hx equals 3x squared dx, and then integral. So this can become hx. This time becomes integral 3x squared dx. So we need to find a function with derivative equals 3x squared. So we know that as cubed. Basic reverse process, okay?
Can we do a few more examples?
Yeah, sure. We can do a couple more example here. So let you use to the, we need some exercise, right? Frank, you're on?
Yes, Dr. Wang. So sorry for missing the first part of the meeting. I think I should be able to jump in on where we are at, though.
Right. You are the learner. Calculus, so it's easy for you.
Yeah.
Okay. Now let's do some interesting. Let's do some interesting. Give a couple example, right? Okay, couple example. So let's say if I have fx equals to x, and fx is a derivative h function. So what is h? So in this case, h is integral x dx. Got it? So which really means equal to what? Can you do that? We already did this, of course. It's a reverse process. We needed, so
Dr. Wang, have you explained to them the concept of a derivative as a limit of tangent slopes?
yes, I did.
Okay.
So basically, derivative is slope, and the integral is basically area underneath that curve to integrate all the way to the point you want to know. So this is basically, we already know. So this function's derivative equals to x, right?
Yeah.
So basically, so that's when the people build all kind of people build the whole set of the formula. Once each one of them they went through this kind of calculation, just like I show you how to calculate derivative, right? How to calculate from sine x, how to calculate x cubed derivative. So people calculate all the way. So basically, eventually, there's lots of formula. Once you know this formula, and you look at the function, you know how to do the derivative. You don't need to go back to calculate delta x approaching to 0, this kind of thing. And meanwhile, once you know a function, you know what function's derivative is this function, then you know how to do integral. Got it? So let's see. So we have a set of formula here for you to play with. So for example, we already know sine x derivative is cosine x, correct? And then if you do the similar deduction, cosine x derivative is minus sine, and then there is actually, you can also calculate this. Ex derivative actually is the same, and log function's derivative actually is 1 over x. All those you can use the original definition to derive it, no problem. Okay. And then of course, then reversely, if you integral cosine x, it is sine x, correct? Function wise. But you have to be careful. Integral, you need to from where to where, and but let's forget about this. Just find this function relationship. The same thing if you integral sine x, will be minus cosine x, because cosine x the derivative is negative sine x. Same thing, you integral 1 over x equals to log x. So those are the basically the some of the formula. You need to when you study or when you use calculus frequently, you will remember them. But you have to understand why how they come from, where they come from. So that remember the derivation we went through. Okay. Any question? I know for the first time, I tried to squeeze the calculus within 2 hours.
That's a lot of calculus.
That's lots of calculus. Yeah.
Yeah, Dr. Wang.
Mm-hmm.
Have you tried to explain like visually why x squared over 2 or 1/2 x squared has a derivative of x?
Yes, we did the so it's like
no, I did a calculation based. I showed them how to do the calculation based on the definition, but I haven't showed them the graphing graphing thing, which
like
is I can quickly go over graphing thing.
It
Did we
might
do
be
like
a bit helpful in terms of helping them to grasp what it is. Like just using like x the line of x and like not even doing any quantitative calculations. You can think about it like if y equals x is like this, right? Or fx equals x is like this. I'm not sure if it's the right direction on your screen, but this means that on this x-axis domain that the y value is increasing as you go to the right and decreasing as you go to the left. And if you take this to be the slope value at any point, then what you have is like the slope, starts out really, really small near the origin and then gets really, really big as you go on. And so visually, it makes sense that x would model the behavior of all of the tangent slopes of x squared over 2. And if they had like a visual like that, so many of the formulas that you just listed make a lot of sense just intuitively. So I was just wondering if that was something that we talked about.
Yeah, each function we can explain. We can give you a graph, picture, understanding is okay. For example, I think I can only go to 20 page. I cannot go more. Somehow it doesn't allow me to go more. I have to erase on the page here. But anyway, I think I recorded I recorded the whole thing. So therefore, so yeah. So basically, let me go back. So to go over one more time, so Frank can look at. Okay. So this is I start to use example of free fall, assuming that within a time t, the free fall distance will be 1/2 g t squared, and you don't need to understand why it's 1/2 g t squared at this moment, right? So go over to calculate what distance traveled at 1 second, 2 seconds, 3 seconds, 4 seconds. From here, basically calculate average speed. For example, at 4 seconds this time, how I know the speed, velocity. So okay, I have to for example use the 4 seconds minus 3 seconds. Within 1 second, I traveled 35 meters. So in our case, if I do this kind of calculation, I came out 35 meters per second. However, if I can use 2 seconds around 4 seconds, I use s 5 seconds at s minus s 3 second distance, and so I came out 40 meters per second. So really means that the average velocity really is variable changeable if you depend on how you pick what segment of time you want to average with. So that is noted for the definition of velocity. So because it means it could be any of them. So eventually it came out to say, okay, let's do the average velocity calculation. However, let's change the delta t to as small as possible. It's around the time point you want to zoom in. So in that case, you do this algebra derivative calculation is give you a pretty straightforward eventually when 30 equals approaching to 0. So you get v actually is dt. Got it? So that basically introduces this slope or tangent or whatever. The basically the change rate, but the change has to be really small around the curve, the place you want to study. So that gives you eventually the definition of the derivative. Okay. So basically, eventually give you a graphing, and give you some example to calculate other function, any random function. You can do the similar thing, and so that eventually so that eventually leading to this picture understanding is graphing understanding is like this, right? So this distance travel with time is 1/2 gt square, and at certain time, and you want to know the velocity, you're basically doing this kind of slope calculation or in tangent calculation, which is tangent theta equals delta s delta t divided by delta t. So that one basically give you try to explain to you the derivative as a slope calculation, and then you do another slope from velocity to acceleration, because acceleration is dv dt, delta v divided by delta t. So that give you constant acceleration. So that's go back to that is derivative. We go back to say, oh, if I really only know that free fall, I have a constant of acceleration g. I don't know anything else. How I can from here to know when I release the ball and at any moment what the velocity is, speed is. So that when you go back. So basically, we already go from top to down this approach. We already understand. Now I have to go from bottom to top one by one. So acceleration, go back to velocity, how to velocity calculate travel distance. So that eventually you do look at the left side, the graph, you are doing basically integral, we call it, is calculate the area underneath the curve to derive this function. So that is what we go back and showing you eventually the integral concept. So integral basically is trying to find a function's derivative, and then you go back. Got it? So that's what we did. We did here, and rest is just the signs that the typical people use this kind of sign to represent what they really mean. So of course, to be able to familiar with this one, we really need you to do some more exercise, and I try to squeeze everything within a 1.5 hours. It's really tough, but you need later on I give you some questions to talk about, some great example, so you can slowly understand what it really means, and then you can grasp this concept. Okay, got it? And so if we, let's say, if we maybe I can save this one. Save in folder. Oh yeah, good. Oh, look like I saved. Wonderful. Cool. Okay, now I can clear my drawing. Okay, cool. So basically, give you a graph understanding. This is x, this is x, a square. This is area is x squared, correct? This function of x squared really means, correct? So derivative really means you want to. So now you have x. You adding a little bit delta x. correct? Then here you're also adding a little bit delta x. Basically, you for a square with x side length x, the area is x squared, right? So that's the function we are interested in right now. Function, okay. So now when the side change by delta x, when x change by delta x, which means side increase by delta x. So what is the new area? The area becomes x plus delta x times x plus delta x, correct? Right? So that's a change. So the change, if we really look at here, is that you're adding three pieces. One piece is this narrow bar. What's the area of this narrow bar? Is x times delta x. What is the other piece of narrow bar? Is x times delta x. Correct? And this place, this little square is delta x squared, delta x times delta x. Correct? So then this is f x plus delta x. And when you say what, I increase side by delta x, what I really change, how much I change really is, of course, you change those shaded area. So that shaded area eventually adding up is 2x times delta x plus a little delta x squared. When this change is really, really small, that is our derivative, the concept. So this one gone is a very small thing, time very small thing is gone. And it left this one, correct? This one has to divide it by the change rate because we are derivative is delta f minus this one divided by delta x. So you see, that's why eventually is 2x is our derivative of x squared. A square's function derivative is 2x. Is in this picture, you understand why, right? It's because it increases, a a narrow bar that is 2x. Area 2x, x times delta x 2 times. The same thing, you can understand why the cube, x cubed derivative is 3x squared. Why? Because if you look at the cube, with side x, when each side increases by delta x, you increase, how much do you increase in volume?
Well, the answer's on the screen.
Right.
X times, delta x cube, I suppose.
Because when this one increase a little bit delta x, you increase a wall here, right? Other side also increase another wall here. And then third side also increase another wall here. You increase 3 wall, each area is x squared. So that's why the derivative is 3 times x squared. Understand? So that's a picture understanding of this. Then the integral is reverse. Okay, it's a reverse process. Okay. Okay, so that's pretty much for this very quick high level of calculus, learning. So maybe next time I try to go over some good example so you can understand. You need a I will send you the record this video. So you need if you need a review, you go review, and there are also really good YouTube teaching on calculus. If you want to watch, I can also send a link. And so next time I will, this is a little bit boring for initial definition of the concept. And but later on, once we learned how to use it, it will become fun to do all kinds of examples I mentioned in the early, right? For example, we can use calculus quickly and calculate the area of a circle pi r square, calculate a sphere surface volume, calculate anything. Which requires a little bit, basically requires the calculus concept really means you need adding small things adding together.
It took you guys an hour and a half to learn what I learned for a year. I'm so jealous.
Okay, yeah. Once you do the example, you will grab it very quickly. Actually, it's no.
Hey, Leo, don't discount your calculus education. You've learned a lot more complicated integrals than the ones that are
exactly,
here.
Exactly.
So don't discount that.
I learned a lot of how to solve FRQs on the AP exam. Namely, the Riemann sums.
But actually, the current screen, this picture of graphic understanding, most schools do not teach you.
Oh yeah.
It's fun to know it's really like that, right?
Yeah. Dr. Wang, could I do like one really quick note?
Mm-hmm.
So there's a YouTube channel called 3 Blue 1 Brown that I've just sent into the chat, and that YouTube channel is all about visuals and making things like calculus and even like beyond more intuitive to understand.
It's
so
from
really
that's
YouTube
from
channel.
Stanford undergraduate guy called Grant Sanderson, I think. Yeah, Grant Sanderson is a great guy. He graduated from Columbia from Stanford Math Department, undergraduate. So he's very interested in teaching. So that's why he created his own YouTube channel, teach all, using graphing to understand all the mathematical concept. So he immediately draw like 2-3 million viewers for each his video. It's impressive. And actually, I sent to some of you before. Try to. He has a great calculus session. I think 12 talks there. It's good to watch. Even though you still go with my class, but it's good to watch. And he has better graphing there, show you how this goes. And meanwhile, he also has called lockdown math, and offered for high schooler, not calculus, but I try to explain. For example, first a video for this called lockdown math from him is talking about how to solve a quadratic equation, and it's quite different what you learn from your school. It's very interesting. The second one, he was talking about, I think he was talking about trigonometry. It's also very unique angle to understand trigonometry, and it's quite interesting too. So you want to watch, I think Frank has sent that link. That's good. So next time I will continue build on this to do some to take some great example, because derivatives is really important. Because the other day Jenny was talking to me, we try to solve try to find a little bit complex functions minimum. And for once you learn derivatives, really easy, because you just right, you just take that function's derivative, because derivative is slope, right? So the minimum really means the slope will be 0, right? So is the maximum. Both maximum minimum where slope will be 0. So that you can find both minimum maximum that way very quickly. So that's one very simple application of derivative. And if you want to further try to distinguish which one is minimum, which one is maximum, after you do the derivative, you do that again, and then you will know which one is minimum, which one is maximum, because the minimum is a slope were basically increase.
Minimum is slow coming
Increase.
from negative to positive, and
Right, that means
maximum
increase.
is-
Slope, you know, you do slope to first derivative again to second derivative will be an increase function around that point. That means it's a minimum. For
I
the
don't think it's
maximum
like-
at going down, right? The slope slowly reduce from left to right. So that is how it's fun. You know, it's a simple application, but it's fun. And the integral, of course, a simple application is find the volume, find the area on the curve, find the volume on the curve, you know, on the surface, and all those sort of things. And then there's lots of physics application coming with that. For example, of course, physics, we know the distance to velocity is first derivative. Second derivative is from velocity to acceleration. So later on, I will teach you how to look at the whole Newton mechanics motion, and with a simple from simple calculus perspective. It's very simple, very easy, very pretty. And so later on, you don't really need to worry about remember all those formula you learned as like, oh, you know, S equals x0 plus you know, v0t plus 1/2 gt squared, this kind of thing. Once you learn derivative, you can easily understand why that is way, right? So there's a lot more interesting stuff you can go with that, which is much harder to describe without learning calculus. Okay, cool. Okay, so that's it for today. And any question, just let me know. And yeah, I will send you the record. Hopefully this recording works. And so I will send you the link. I have to put on the YouTube so you can watch them. And any question, let me know. And hope you enjoy it. Okay, great.
Thank you so much.
Thank you.
Thank you so much.
Okay, bye-bye.
Bye.